Hello everyone. Today is the 60th day of Leetcode 75 challenge. Let's begin with the 60th question. Question 746, minimum cost climbing stairs. The level of the problem is easy. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. You are given an integer array cost where cost of I represents the cost of stepping on the ith stair. Okay, you can start from step 0 or step 1. At each move you can climb either one or two steps. So basically what they're trying to say is that suppose if this is a step of array of steps containing steps, right? And this is value 1. Let it be I'm writing some random values here. Okay, this is the end. Okay, so what they are saying that you are given an integer array cost where cost of I represents the cost of stepping on ith stair. So this is what is given to us. Okay, 1 2 3 4. Okay, so this is I have converted to a stair. So and this particular value represents the cost of stepping on that particular stair. Okay, and they are saying that you can start from 0 or step 1. So 0 means what? Suppose if you are standing here, this is a 0th step. You're just going to the adjacent step, right? Or you could say step 1. Step 1 means from here you directly started from here. Okay, so either you can start from here or you can start from here. These are the two ways you can start. And your goal is to reach the top of the floor just beyond the last stair with the minimum total cost. You do not pay any cost for the final move that takes you beyond the last stair. Okay, and also here it is written that you can climb either one step or two steps. Suppose if you're standing here, they're trying to say that either you could jump here or here from this particular line, right? Then therefore also if you're standing in here, you can take one step or you could dive to two steps. So this is the way you are going to perform the climbing of stairs. And also they are saying that if you are standing here and you cross this, instead of coming here you directly take two steps and you reached here, you don't have to count this step. Okay, so that is what they're trying to say, and we have to find the minimum cost to reach the top. That's all. Okay, the constraints of the problems are the cost array length is from 2 to 1000 and the value of each step could be from 0 to 999. Okay, so I hope you understood the problem explanation. It was pretty straightforward and simple. Let's move to the next slide. Now let's understand the input output explanation. So if you take this example here, it's 100, then 1 1 1, then again 100, 1 comma 100, then 1. Okay, so if I'm standing here, okay, so if I take this step first, if I write s1, that means I have taken one step. If I write s2, that means I have taken two steps. Okay, and then from here if I take step 2, two steps, I'm skipping this, I'm taking two steps, then I'm trying to take step 1, then again step 1, then from here, let me remove this, I have taken this wrong. Okay, and from here I took step 2. Now from here I will take again step 2. Okay, then from here again I will take step 2, then step 1, and then step 2. The total sum comes out to be 1 2 3 4 5 6, right? What if I have taken step 1, then here step 2, great, then again step 1, then again step 1, then from here step 2, then again step 1, then again step 2. The total count would have been 3 4 5 6 7, right? So this way we have to check multiple ways of taking out the steps, combination of steps I would say, and from that you have to kind of find the minimum. So here this is the minimum one which we have initially checked. Okay, so I hope you understood this example. Let's understand this example too also. So if this is what is given to us, 10 15 and 20. Okay, so if you start from here and you say okay, 10 looks smaller, so I will take 10 first, which is step 1. And here if I can see, if I take step 1 again, I get 15, which is less than 20. Then from here I will take step 2 and I will come out, so total sum comes out to be 25. Okay, fine. But another person says no, that I will take step 2 from initially, I will land at 15, and from here again I will take step 2, then I will land outside of the array. Okay, so he gets the result in 15. So which is minimum? 15, right? So that is why the output is 15 here. Okay. So I hope you understood the input output explanation. Let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem. So let's do that by understanding the goal first. We are given an integer array cost where cost of I represents the cost of stepping on the ith stair. Okay, we have the understanding of this now clear. From the ground, we can either take start at step 0 or step 1. This is also clear to us. Either we could start from here itself or we can start from the second step itself. At each step, we can move one or two stairs ahead. So with the, we can either take, if you're standing here, I can take one step or we can take two steps from here. Okay. The goal is to reach the top of the flow just past the last stair with a minimum total cost. We want to find the minimum cost to reach the top, not necessarily to land exactly on the last index. Okay, this is it's clear to us. Now, what is a brute force? A brute force approach would recursively explore all paths by trying both one step and two step moves at each step. Why recursion, if you ask me? Because here we have to find multiple ways, right? Multiple ways to get our answer. First thing. Second thing, we have to find from multiple ways which is the minimum cost, right? This is another way of figuring out that since we have to explore all the possible results in this particular staircase question, we have to use recursion, otherwise it won't be a possible thing for us. Now time complexity for this will become 2 to the power n. Reason being, for each step we have two ways, either we could go one step or either we could go two steps, right? So this is what the problem is all about. Let's move to the next slide. Okay, so let's try to visualize the process. So before visualizing, let's take an example of this itself, 10, 15, and then it was, I guess, 20, right? Let's take this example itself. Okay. So let it be 0, 1, 2 index. Okay. Suppose you're standing at -1 index with sum as 0, right? Now what will happen? You have two options, either S1 taking step 1 or S2 either taking skipping two steps, right? So if you take one step, what will happen? So you will come to 0th index and the sum will become 10, right? And if you go for the two step part, so the index will become 1 and the sum will become 15, right? Okay. Again, if you come here, again two options we have from here, right? If we take one step again, the index will be 1 and the sum will be 25, right? And if you skip basically one step, then we will be standing at index 2 with sum as 30. Okay. Again, out of that, if you take another step, you're just going step by step here, right? The sum becomes 45. Now this is the end. Okay. And if you skip it, right, from one you directly jumped two steps, then what will happen? This will be n because you came out of the, the array, and the sum will remain 25 itself, right? Okay. so, so if we compare from this to what is the minimum, it's 25, right? We will do that later, wait. So here, okay, so here you went to left means since you were already at index 2, so if you go outside there would be if you go one step ahead also, then also there will be nothing. It will be n basically, which means that you came out of the array. The sum remains 30. It is 30, yeah, it is 30. Similarly here also, if you take two steps, then also it will be out of the range and the sum will remain 30. So this is the ending point to us. Okay. Now here, if you take another step from here, the index will be 2 and 15 plus 20 will give me 35, right? So this is our end. If you can see, this is our end. Okay. And here, if you skip this part from 1, you directly came outside, it became n and sum remains 15, right? I hope you got that. Now if here you can see, if you compare these two, it will return 25 minimum, right? These two are 30, so this will definitely return 30. Okay. Comparing 25 and 30, it returns 25, right? Now coming back here, 35 and 15, right? So minimum of 35 and 15 is 15, definitely. Now it has 25 and 15 with it. What is the minimum? It's 15. So this finally will return 15 to us. Now we have observed this recursion carefully, that how the recursion will work and how the steps will be going, right? So if you can see, is there any repetitive problems? We, in this particular scenario, we are not getting repetitive parts, right? But yeah, in this problem we don't have any repetitive part. But if we take any other example, there might definitely be a case where you might get repetitive solutions, like 35 is called again and again. Like here you could see 30 is called two times, right, in the, both the scenarios, and similarly the others also. So in that part, we what we need to use, we need to use dynamic programming, right? Since recursion is not the solution to our problem, as we discussed earlier, because the time complexity which is takes is exponential, and which is more than the constraint which is given to us, right? So for that, if you can see, we have just compared these steps, right? Where is the share I? You essentially have two options: either we take one step or we take two steps, right? So these points are clear. You can have a read of it, but the observe leads to a repeating pattern. To calculate the cost at any step, we need to know the cheapest cost to get the previous two steps. Therefore, we need DP. That is what I explained earlier. In the example which I took, there were no uh, repeating patterns, unfortunately. But if we have, we will be having repeating patterns if we take the bigger examples, okay. And to get the cheaper cost, we need to take the cheaper cost beforehand, right? Which is what I have written here, or the previous two steps or previous one step, whatever. So to have that, and to reduce the time complexity, and to not to recalculate the same thing again, suppose in index 2 you got 30, right, and somewhere else in index 3 also you got 30, and here you will know that okay, the sum will come out to be same. So why we will calculate that again? For, and but if the second step comes out to be minimum after 30, to know about that, we need to have the value 30 with us, right? So this is what is all about. That's why we try to use dynamic programming here. Now how will the equation will look like, right? That's the important part. Suppose if you take step 1, okay, what you're doing, you're taking the cost of I which you have, and then what you're doing, you're calling some function, and you're doing I minus 1, okay, because in this scenario I have started from the n, okay, or you could say I plus 1, anything. Or if you take step 2, it's cost of I wherever you're standing, and you just skip the steps, so you do I plus 2, or it's I minus 2 if you start from the back. In this particular solution, I have started from n rather than 0, okay. And after that, we will just compare the minimum of step 1 and step 2, and that will be our answer, okay. So I hope you understood the visualization process. Let's move to the next slide. Now how we can simulate this process? So that will be done just very easily. We will just define a function which is basically a helper function or recursive function, which will have the cost array with it, the dp which we will create, and the index, the current index, right? And you will be thinking how the dp array will look like. Dp array will be simple as that. It will be minus 1 multiplied by n plus 1, because it's a one base indexing, okay. And also about the base cases, if you're starting from n, I'm doing n minus 1 or n minus 2, right? N minus 1 or n minus 2. So if you are standing at n equals to 0, suppose, what that means? That means that this was a stair and this is the ending here. So standing here, right? So you have to take this value, you have to take it in account, okay. So what you will do for that, you will return n. And if you're standing here, and somewhat from here you know that you will go two steps rather than going one step, what you will do, you will return the one value directly, right? So that is what the base case is all about here. And also, since we're using dp, and so we don't calculate the same sum again and again, what you do, when standing at dp of index, if it is not equals to minus 1, that means that we already have some value for this particular index, right? So return from there itself. And I just told you about the recursion which we will write. You could write either answer or you could write fun, whatever you want. This is the dp is passed here. No, that's all, okay. So this is how we're going to simulate this. We will understand much more about the code in the upcoming slides. Let's move to the next slide. What we figured out? We figured out a plain recursive approach without memoization leads to an exponential time complexity. That is clear to us. Using memoization, DP stores already computed results and avoids recomputation. This is the benefit of using a DP. This brings down the time complexity to a linear and makes the solution scalable to a large input sizes. In the dynamic programming approach, here guarantees that we compute cost for each step only once, right? Since for step 2 we were calculating multiple times or 2 times at least, right? That either from suppose from step index x, either you were going 2 steps or you were going 1 steps, right? So instead of doing calculating that again and again, we use DP. Okay. So I hope you understood the intuition explanation. Let's move to the next slide. Now, since we got the intuition of the problem, let's look into the approach how we're gonna solve it. Let's start by handling the base case in the function which we will create, the recursive function, fun or answer, whatever name you could give to it. In that, if you remember, we were passing DP, cost, and index, right? This index starts from n minus 1, right? We know that. So, in our base case fun, suppose this is a function, we will write index. If it is equals to 0, just return index. If index is equals to 1, return cost of 1. Here I meant cost of 1 actually, cost of 0. Okay. So this way the base case is fulfilled, and this means that these are the base steps. Reaching step 0 or step 1 means you directly pay the cost at that step without any previous decision. Okay. Now step 2, preparing for memoization. In the main function which will be given to us, base function, in that we'll initialize a DP of size with minus 1 with n. We are doing zero based indexing here. Okay. So why this store the minimum cost to reach each step and help avoid redundant computations. Fine. Now at step 3, we'll add a main recursive logic inside fun. Okay, the main function. This is the base case I already talked about. This is the memoization check which we will be doing, and this is the main compute. Here we will calculate the sum for step 1 or step 2, and then in DP of that particular index where we are standing at, we will take the minimum of step 1 and step 2 and store it here, and then after that we will just return that particular DP to the above calls. Okay, this ensures that each state is solved once and cached, reducing overall time complexity. And after doing all the recursive calls and stuffs in the base function, we already know that we call the fun, okay, or answer, whatever the function name is. If you can see, we are having two ways. Why? Because if you remember, either we could start from here itself, right, or we could start from step 2 itself, right? So if what, so one function calculates the answer for if we take step 1 rather than step 2, and the second one compares if we take directly start from step 2, and then we try to compare the minimum of both of the function calls. Okay, so this results the final output. So I hope you understood the approach explanation. Now let's move to the next slide. The code is the exact copy of the approach discussed. Let's understand it line by line. So the code is the exact copy. If you can see, we just taken the length, we have initialized the DP, we have called the function for with n minus 1 step and n minus 2 steps, then we're comparing it with the minimum. Okay, now this is the base cases, and then this is the DP call, DP case for the, so that we don't go and calculate the repetitive values again and again. And after that we have step 1 and step 2, and we calculate the sum here, and we compare the minimum and store it in the DP index, and we just return the DP from here. Now the time complexity, which was 2 to the power n before, is boiled down to O of n. Why? Because here we are only calculating the cost for its index one time itself. There are no more repetitive calls. Okay, that is why time complexity boils down to O of n, and space complexity boils down to O of n, because we are initialized the DP array of size n, which is equal to the size of the cost array. Okay, so I hope you understood the code explanation. Now let's move to the next slide. Now, since we have the understanding of the code, let's look at the dry run of the example. So for our better understanding, I have also brought down the code here. So let's try the dry run. Okay, let me create a DP array first of size n. Okay, So let's go for the try run. Okay, so we started here with first n minus 1. Okay, so how do I do it? Okay, so this is a recursion tree. Suppose this is a recursion tree. Okay, and it starts with n minus 1, which means the index 2 and there is a value 20 with it. Okay, great. Now we call the n minus 1 function, which means that you are here, right? So you took the 20. First of all, this base case got false because you can see that index is not 0, and dp of 2 is also is equals to minus 1. So what you do in step 1, what you have 20 plus, and you call the function call, which means that here you got 20 with you and you call the function 1. Okay, so again this happens and you come here and you say that yeah, index is 1. So we just return the cost of 1. What is cost of 1? Which is 15, right? So as soon as you return, this function call returns 15, right? So this means that this function call returns how much? 35, right? So step 1, let me write it here. One value was 15, right? So here after adding this it returns 35. Okay, 20 is coming from above. Now but step 2, what happens if you calculated the step 1 from here, right? So you got 35. Let me tell it clearly. So you had 1 because you took 1 and you got 35 here, right? And you just return from here. That's why I'm not reducing the index. Okay, what if you have you know, you have done n minus 2. Since you were standing here, you did n minus 2 means you came here, right? So the step I have written writing it as 0, and it becomes how much? It becomes 30, right? So you have 35 and 30 and you return the minimum of worth of it, which is 30, right? So for dp of 2 you get 30, because when this is done you get the minimum or dp of index where we started with 20, right? Second index, right? So you return dp of index, which is 30. Now this is done. But now what happens if this function call is complete, right? Now this function call is done, n minus 2. So from 2, not exactly from 2, n minus 2 means what? N minus 2 means you're starting with 15, right? So I will write n minus 2 is how much? N is 3, n minus 2 is 1, right? So for 1 you have it here and you got to 15 in the sum, right? Then again you have two options. But since, one more thing, since you call this, we came here, we say okay, yeah, index of 1 is equals to, since it is index is equals to 1, right? Here in this scenario, so what do? You return cost of 1. Instead of calling the functions again in deeper, you already started with the index 1. I think that is understandable to you, and the base case is here. And as soon as you get the base case, what you return the cost of 1. Cost of 1 is 15 here, right? So you try to return 15 from here. So this function call is completed. Okay, and dp of index from here returns 15. Okay, so dp of index was 1, so it returns 15. Okay, and when we come back here, we have 30 in one hand and we have 15 in one hand, right? And so minimum of this 2 is what? 15, right? Definitely. So you get a 15 as the output. I know the recursion call was shorter, it might could have been a bigger one, but for your understanding and for taking less time, I have just taken the smaller example. If you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition, the approach, and the code. And also, if you are weak at recursion, please go and read about recursions. After that, do try run by yourself on 2 3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. Now, let's move to the next slide. Now, since you're familiar with the problem and the solution, let's move to the lead code and code the solution. We will start by initializing the, or by taking the length of the cost array, then initializing the dp array with minus 1 into n. Then we will return the minimum of self dot, what should be the function name? Answer or fun? Let it be fun. Okay, so cost of the cost and dp, then we will pass n minus 1 here and self dot fun We will pass cost dp and minus 2 here. We will create the fun function here now, self comma cost comma dp comma index. Okay, now base case, if index is 0, just return cost of 0 from there. If index is equals to 1, just return cost of 1 from there. Else if dp of that particular index is not equals to minus 1, that means we have already have the answer for that. So we just return dp of index from there, and otherwise we calculate step 1, which is cost of index plus self dot fun. We have the cost. Okay, we have the dp, we have now index minus 1. We take one step. Okay, now for the step 2, what we will do, we will take two steps, right? Then we will calculate the dp, the particular index what we have, minimum of step 1 and step 2. Okay, and we will return dp of index from there. Let's try submitting for the sample test cases. Okay, there's an syntax error. Try again. Let's finally submit for all test cases. So we have successfully submitted our solution. Now code of the problem is available in my GitHub repository. You can find the link in the description. Thank you everyone.